Andrey, can you hear us?
Yes, yes.
Okay, yeah.
Just. Okay. Here it is. Okay. Just one more thing. Okay. So, sorry, this is the beginning of the lecture. So, today we're going to talk about left symmetric algebras. These are very specific objects, and this is one of them. These objects are the ones that correspond to the next simplest left symmetric, okay, if you imagine the simplest Nijenhuis operator, then it will be constant Nijenhuis operator, okay? Because Nijenhuis torsion for constant operators vanishes because it is a linear combination of operators and their derivatives. But if you think about the next best thing, like something a little bit more complicated than constant operator, this will be an operator with a linear dependence on coordinates. Same thing happens in Poisson geometry, we'll get to it, and the case of linear dependence in Nijenhuis geometry, this is closely related to so-called left symmetric algebras. I'm sorry, someone's making noises. Can you please mute? Okay. No, I still can hear. Okay, but I think you've heard me. So, what is left symmetric algebras? Left symmetric algebra, there'll be a little bit of algebra today. Well, left symmetric algebra, we will discuss only algebras over field R on C, real numbers or complex. And this algebra is a simple thing. You have a vector space, and you define an operation on vectors. And this operation needs to respect the addition of vectors and the multiplication of vectors by number. It means that this operation should be bilinear, and if and bilinearity is enough. Okay, and it should be, I think it should, yeah, bilinearity is enough. So the associator, if you can come up with any operation, for example, you can take all the vectors and define their multiplication as being zero, like you multiply any two vectors, you get a zero vector. It's a really good multiplication, but it's called trivial because it satisfies it satisfies different nice conditions, but we call it trivial. And not only us, but all the algebraists. The most interesting algebras are usually Lie algebras and associative algebras. But left symmetric algebras, they're neither one nor two, but we'll see that they go somewhere in between. So first we need to define an associator. Here it is, using calligraphic A. This is exactly the associativity condition. If you equate it to zero and say, well, assume that this part always vanishes, then, well, you get an associative condition. It means that your algebra is associative. Example of associative algebra is matrix algebra, for example. Okay, but if it does not vanish for all the triples, then your algebra is not associative. Here, that's what we do. We call an algebra left symmetric if its associator does not vanish. Well, it might vanish, but we put a lighter condition. We say that if you take this argument and this argument, then you can switch them. See? This is called left symmetry. Well, basically, you take three arguments. You take first and second from the left, and you can switch them, and it stays the associator. It does not change. We see that if associator vanishes, then it's obviously, this condition obviously holds because it is 0 here and it is 0 here. But well, we would, and it shows that left symmetric algebras is a large collection of algebras, right? We have associative algebras including this class. So this class is rather large. Okay. So here's some examples. Later we will deal with the finite dimensional left symmetric algebras, and they naturally appear in very many different contexts. For example, they appear in study of homogeneous cones. That is how they were discovered by Winberg, and also they were studied by Kazul. So they are sometimes called Kazul-Winberg algebras or Kazul algebras, or sometimes they are called Pre-Lie algebras. We'll see why. And but very often they appear in infinite dimensional constructions, like when you have a infinite dimensional algebra. Sometimes these constructions are rather important. For example, this one. If you consider a pair of functions, then you can define a multiplication which goes like this. This multiplication, you see, you take f and g and you multiply f not by g, right? But the derivative of g in x. This operation like this, but you still get a function. Okay, and if you now you can do the calculation of associator straight ahead. Here it is. GH is gives us GHX. Then FG gives us FGX. Then here we need to differentiate this and multiply, and we get this, right? And here we need to differentiate this, and by Leibniz rule, we get that we'll get gx and h second derivative in x. See, and those cancel out, and we get as the following condition. So the associator yields the following. We see that this associator, it is symmetric if we switch f and g. If we change places, we'll see that this associator does not change, right? So this is in fact left symmetric algebra. This left symmetric algebra is a nice algebra. Keep it in mind. We'll see later that this algebra naturally appears in a very specific context of differential geometry. The second example, it is more geometric. If you take a manifold and with a flat symmetric connection, and if you can define an operation on a vector field which goes like this. Flat means that its curvature tensor vanishes, and symmetric means that the corresponding Christoffel symbols are symmetric, or if you if you look at this formula, this is supposed to equal to the commutators. This is the vanishing of the torsion. This is a torsion tensor. So we can define an operation like this. You take a vector field, one vector field, another vector field, and you take a covariant derivative of one vector field along the other. This will be the multiplication, see? And then you can write down the associator. It goes like this. We apply, here it is first you apply to zeta at eta and then psi, and then you apply to zeta xi and which were applied to eta, see, like this. It means this is the argument. This is like the covariant derivative of zeta along the vector field, which itself is a covariant derivative of eta along psi. And this is the associator. It's not straight ahead obvious that it is left symmetric, but if we write the left symmetry condition, we just write associator like this, and we subtract the associator with a eta and z in psi switched, we get the following condition. We see that we get this and this, because in this argument the covariant derivative is linear, right? And we know that because we have a symmetry condition, it means that the covariant derivative is symmetric, the Christoffel symbols, then we can replace it with just psi eta, which is actually commutator, just simple usual commutator, which has nothing to do with the connection. And then we get this formula, which is quite a well-known formula for the curvature of the torsion of the connection. This is just Riemann curvature of the connection, and we see that because we have a flat condition, that condition of flatness, that means that the tensor vanishes and this equals to 0. See, so we have a very nice operation. We see that left symmetry, if you have a flat symmetric connection, then you have a infinite dimensional left symmetric algebra behind it. You can go a little bit further and consider not all the connections, but for example, the connections that are invariant with respect to action of some group, and you will get left symmetric structures on the orbits of the action of the group. And if you take the adjoint action, then you will get a left symmetric algebra structure on the Lie algebra, with the interesting property that the commutator with respect to this structure is actually a Lie algebra commutator we started with. And this is actually the way Weinberg discovered these algebras. He actually studied this situation in more specific case when your manifold is not your arbitrary manifold, flat manifold, but actually a Lie group. Okay. So the next proposition is the main property of the left symmetric algebras, why they are so important. And because this is such an important condition, we prove it here in details. Again, keep in mind that this is a commutator vector field. It relates to this example, and this is already a different operation. It is a commutator just defined using this formula. So we take left symmetric algebra and define a commutator. Same way you do, for example, in matrix algebra. You can multiply matrices and you define commutator as AB minus BA, the commutator of A and B. So you take this commutator as a definition and you look at the Jacobi identity straight ahead. So what you do, you write like this. First you open the inside bracket. See, it goes like this, and like this. It's very similar to the proof that Jacobi condition holds for the multiplication of operators, but the multiplication of operators, it is associative. And when you open all the brackets, you need to leave when you open all the square brackets, you need to leave all the round brackets, because your operation is not associative. It means that if I take sine multiplied by this from the left, right, this is not the same. This is not the same as I took psi eta, where it is psi eta, and multiply it by zeta. See, this and this, they are the same if we deal with an associative operation, for example, multiplication of operators, but they are not the same if our operation is not associative. And usually when you prove the Jacobi condition in case of operators, they just cancel out and you write 0 here. But what we do not write 0. We see that, well, we can rewrite the Jacobi condition for such operation in terms of associators. This formula, it holds for arbitrary operation. It has nothing to do with the left symmetry yet. So if you take arbitrary algebra with arbitrary operation and you ask yourself, does it satisfy the Jacobi identity? And you write the Jacobi identity, you get that, for example, you get the following formula. You see, what is this formula about? This formula works like this. You take a triple of elements psi, eta, and zeta, then you do the switching and you do the substitution of this element, and you multiply the associator by the sign of this substitution, right? So, for example, here we switch these two, and this is a simple transposition, and means that it has a degree -1, like odd degree. So we write -1, and then we can switch these two, right, to get this one, and again we get -1, and this will again yields us +1. Then we do again the switching, and yields us -1. Then we do again this switching, +1. So it is an alternated sum of associators. It's a general property. You should always keep it in mind. And we see that the left symmetry condition is like a simple condition that allows this sum to vanish, because what we have here is we have that if you transpose two of the elements in associator, it is supposed to they stay the same because of the left symmetry, but they belong to this formula with a different signs because it's transposition, right? So it's the same way you can prove that if you have a right symmetric algebra, which means that you can switch not first and second, but second and third elements. And you can, for example, switch first and third element again, like this, whatever, central symmetry condition. So both in all these cases, you get that the sum vanishes and you get 0. It means that the commutator satisfies the Jacobi condition. Okay. So now we need several structures. We will use it. We will use them later. Okay. So the first structure is like this. If you have an operator, if you have a pair of elements, psi, eta, you can multiply them, and this defines a sort of left action and right action on the algebra itself. So you take L eta and multiply it, and this left action means that we multiply it by psi from the left. And right action implies that we multiply psi by eta from the right, okay? If we deal with associative algebras, for example, these are good representations. They call the right and left multiplication representation. They're really nice. And it means that you can represent your elements L and R as elements of as matrices. But in our case, they are not representation because we do not have associativity in general. So these actions, both left and right, they do have different meanings, but still they quite meaningful. And let's get to this. First, let's look at the left action. That is what people who study left symmetric algebras usually do. Because if you look at the left action, well, you can write it like this. Look at the left symmetry condition. This is simply associator minus another associator with a switched eta and psi equals to 0. Okay, what do we have here? Look, we have zeta, and we have left action of eta, and we have left action of psi. So we can rewrite it like this. If we look here, we see that zeta, and we have left action of psi and left action of eta, right? And we write it like this. And here we have left action on zeta by multiplication of psi times eta, and here eta times psi. So if we subtract them by linearity, we get that this is exactly the commutator. The commutator we have defined earlier, this commutator on algebra. And we see that we get the following really nice formula. We see that the left symmetry in terms of this left action, right, of the algebra on itself is actually, right, a representation of Lie algebra. It means that these elements, these matrices which you obtain, they depend from point to point, but if you commute them, you get the element from the same family, right? When I say action, I mean like you have a family of operators which are defined for each element. And we see that because of the left symmetry condition, these operators, they do possess a nice structure, the structure of Lie algebra. But if we want to write something for the right action, like the family of operators for left symmetric algebra, which are acting on the right, again, it's like the family, this family of operator. We'll see that in algebraic form, there is not much to write. If we try to rewrite this formula, we get something like this, right? So this is basically for the Xi, this is this, and then you write it like this, and well, it's it doesn't look interesting. So let's see, we interchanged the names of the variables. So we see that we have a mix of left, those matrices which we obtained from the left action and the right action. So it turns out that you need to look at this family of operators from a different point of view. Okay. Let A be a finite dimensional algebra, which means its dimension is not an infinite. Okay, then we know that it has a natural structure of affine manifold. Okay, it's true because we deal with algebras over the field of real and complex numbers. In general, does not necessarily carry an affine structure, but in our case it does, because, well, what we say that we can take an affine structure, we can take an affine space with an associated tangent space with associated vector space being our algebra, and this automatically defines us a collection of points. We have topology, we have a and we have a nice property. Then the tangent space in each point of this affine algebra is associated with the algebra itself. Okay, when I say affine algebra, I mean affine space which we obtained from algebra, because affine algebra it usually means different. Okay, so I'll be careful with my terminology. So that is what we get. We get an affine space with a structure of algebra. Now, now what we do with the what we do next? Next, we consider a point. We consider a point on this manifold eta, and again, as I told you, the tangent space at this point, it is associated with algebra naturally, right? This means that it is an affine space that you can relate all the tangent spaces using canonical affine connection, right? Which in our coordinates is obviously 0. Okay, and I say, well, at point eta, if we take at point eta and we take an element Xi from tangent space, then I will define an operator field. Okay, so I will say that, well, basically what we get? We get that we have a family of operators. To each point, it is an operator associated to it. Then basically we defined an operator field. Okay, still very nice. And we say that it acts like this at point eta, applying to the vector Xi from the tangent space. It's just the right multiplication by it. Okay, so we get that this right action, this right family, can be understood as a operator field. Same goes actually for the L. We will use our understanding of L as operator field, right? And it means that just at point eta, Xi, and you just switch them around and you get the same for L. And we see that this is an operator field. It's not a map into the matrices, because it can be understood as map, of course, but this map does not carry, the image of the map does not carry any nice algebraic structure. So, and we get this nice theorem by Winterhalter, which states that the algebra is left symmetric if and only if the associated operator field we have just constructed using this formula is Nijenhuis. See, it's a very, very nice observation, which actually says that, well, if you want to understand left symmetric algebras in terms of algebra, then you have left action and you have this nice map into the Lie algebra, right? But it says that the right action, it also carries a lot of information about the left symmetric algebra, and this information is geometric. See, it's a very interesting object, because you have, from one hand, you have a purely algebraic structure like Lie, with associated Lie algebra structure, and from the other hand, you have a purely geometric structure. This basically, you have a operator field. So let's prove this Winterhalter theorem. It's not very complicated. So we fix bases, right, in algebra and associated coordinates, affine coordinates. And in these affine coordinates, we see that, well, basically, if you look at this operator, then it satisfies this condition by this. So you just need to substitute instead of eta the decomposition into the coordinates, usually with the basis vector field, and you apply to psi, and you get that it acts like this. And we see that this is the good operator field, and it depends linearly on the coordinates. See, it's another another thing with terminology, that we have a linear operator actually, because it acts on linear space, right? It's linear with respect to the structure on the linear space. And from the other hand, we have an operator field which is linear in coordinates, which means that its entries are homogeneous linear polynomials. Those two linearities, they're absolutely different. They have nothing, a little in common. One has to do with the coordinates and normal form of a tensor field. The other has to do with the nature of this tensor field, right? That we have a one tensor field. But this observation is nice, because if we look at the now we look at the Nijenhuis torsion of this operator, then we will see that it is a linear function. Why? Because these are homogeneous linear functions, and these derivatives are constants, right? So if we multiply them and gather all the terms, we get the homogeneous linear components for our Nijenhuis torsion. So what we do is we take the derivative of this Nijenhuis torsion, and we get the following formula. These are the structure constant of the operator of the left symmetric algebra we started with. Okay, we see that this, in terms of basis vector fields, can be rewritten like this, and this is exactly the associator condition. So the final step of the proof, it goes like this. Well, look at this. If the algebra is left symmetric, then this vanishes, and it means that all derivatives, they identically vanish. And because the components were homogeneous linear polynomials, they identically vanish, which means that the Nijenhuis torsion vanishes. This implies that if we have a left symmetric algebra, then the corresponding associated right operator, it is Nijenhuis. And now the other way, it's even simpler. If this torsion vanishes, then associator is left symmetric. So we have shown that the left symmetric, I'm sorry, there's a typo here. It's supposed to be space. So we have shown that basically, if you have a linear operator on then affine space, not linear in a sense that it's tensor 1, 1, but it depends linearly on coordinates. So you have an operator field which depends linearly on the coordinates. Then you do have some algebra structure. Moreover, if you have a linear operator which is Nijenhuis, then you have a left symmetric algebra. So it shows that we have a huge number of Nijenhuis operators. See, because from before we tried to look at the operators, we look at their normal forms, and we saw that they come from different linear algebra, like Jordan block, diagonal form. And here we have a huge collection of Nijenhuis operators that come from absolutely different setup. They do come from the left symmetric algebras, in particular because we have a an associative algebra, and it is being left symmetric. Then it means that if you take any associative algebra and you take this right multiplication, and you get an operator field, and this operator field must be Nijenhuis. So you can. It is a very nice observation. It means that we have a lot of there are a lot of associative algebras, if you didn't know. So there is a huge collection of operators. But what is more important, we have established an important equality, we say, well, studying the left-symmetric algebras, is basically the studying homogeneous Nijenhuis operators of degree 1, which means that we have a Nijenhuis operator on a affine space and it has degree 1 in terms of its coordinates, right? It's polynomial and its entries are homogeneous polynomials of degree 1. And we see that this condition, it is this observation, it is rather important, because if you remember the earlier lectures, the ones we started with, we actually discussed that very often we have discussed, I'm sorry, what did I do? Okay. We discussed that there is a certain parallels between, for example, Poisson geometry and Nijenhuis geometry. And this is one of these important parallels, not in terms of science. Of course, they're quite different in terms of theorems, in terms of techniques we use, but they are parallel in their development. And this is a good example, because if you there is a natural, the similar identification comes in Poisson geometry. We say that if you have a finite dimensional Lie algebra, then there is a natural affine structure on both Lie algebra itself and its dual space, if you have a Lie algebra, then you can define a bivector which acts like this. Look at this formula. It means that at point in the dual space, in point x, at point x, it acts on a pair of vectors, which are actual elements of this space, but because of the finite dimension, we have this, right? Because we have identified this tangent space with G star, which means tangent star is identified with G2 stars, and G2 stars is identified with G. So we say that these elements, they're actually elements of algebra, so we can commute them. This is a commutator in the sense of this Lie algebra G, and apply this covector x. And we get this following bivector. It's skew-symmetric, it depends on point. If we write it in local coordinates, we will see that its components are homogeneous linear polynomials. So this is a linear Poisson bracket. And we'll see that these linear Poisson brackets are in one-to-one correspondence with Lie algebras, because every such linear Poisson bracket on a affine space is nothing more than as some Poisson structure defined in the following way on the space dual to some Lie algebra. This is important because this observation allows some insights into the geometry of Lie algebras, because for example, it is from this observation it is easy to see that coadjoint orbits, they must be of even dimension, for example, which is not obvious from the start if you just write a Lie algebra. So this observation is quite useful. It allows you to get some insights. So basically, when we use this observation, that is what we want to do. We want to get some insights into the left symmetric algebras, and we want to get some insights from the left symmetric algebra, which also happens because, well, if you look at the Lie algebras, then what is your first idea? Well, you have a different classes of Lie algebras. For example, you have semi-simple Lie algebras or simple Lie algebras. You have compact Lie algebras, and all those classes, they are interesting on their own, and they have very specific geometry. So the natural question is, well, can we apply something we know about Lie algebra to the affine structure? And of course, the answer is yes. Yes, we will see it in the later lectures. And the same idea goes here. If we know something about left symmetric algebra, maybe we can apply the information we know about left symmetric algebra to the knowledge of Nijenhuis geometry. Okay. So now the rest of the lecture will be dedicated to the proof of classification theorem. It is a really large theorems, and the proof is long, and it consists of carefully checking a lot of cases, right? Now, what I will be doing, I will be all these cases, they are written in the presentation. So if you will have a desire to check my calculations and to see how this proof works in detail, you can, because when these lectures will appear online. But for now, we will just concentrate on several cases, and some of parts of the proof we will go over pretty fast. So don't be scared. I'm rushing not because I think it's obvious and you do not need to understand all the details right now. You can understand them later when you go over the presentation. Because, well, the main idea here in this lecture for me now is to show you the specifics, like where the classification, where important stuff happens, and where the rest is just careful case-by-case checking. Okay, so we start with a simple observation. It is an example. We classify all one-dimensional algebras. As I said before, what is algebra? It's an operation. If you take two vectors, you multiply them, and you get another vector. In case of one dimension, if you take two numbers and you multiply them, you get the same vector multiplied by some number a. Okay. If a is 0, then we have a trivial algebra. We've discussed it. The trivial multiplication is okay, and it is commutative. Then if a is not 0, then we can take the following coordinate change. See, that's what we do. We take eta barred, and then we do the computation. We multiply eta bar by eta bar. It means that we open. Using linearity, we get that it is supposed to be divided by 1 over a squared. And we got eta times eta multiplied star, which is a eta, and we substitute it here, and we see that in the end we get 1 over a eta, and this is exactly eta bar. So we get that is in u coordinates, the multiplication is like this. You take two elements, multiply, and get the same element, which means that in dimension 1 we have basically two algebras. They all are commutative and they all are associative, right? So because of the construction, you need to check the commutativity and associativity on the basis vector field, and if you do that for eta, you'll get 0. For the trivial algebra, you will get 0. For this, you will get eta on both sides, and you see that it's associative. Okay, so they're obviously left symmetrical. And now we consider the two-dimensional case. This is the vast and complicated. Interesting thing is that if you want to classify the Lie algebras, you start with the dimension 2, because it's very simple to do the classification. You have two Lie algebras, which is one is commutative Lie algebra. It means that the commutator vanishes, like same as trivial algebra we dealt with earlier. This is the trivial algebra. And then you have a commutator which, after coordinate change, can be brought to the following form, like eta 1 times eta 2, like a commutator with eta 2 equals eta 1. So we get that there are very few Lie algebras in dimension 2. But it turns out that there are a lot of left symmetric algebras. We remember that there is because if you have a left symmetric algebra, then you can take the commutator and you get Lie algebra. So basically, if you take any left symmetric algebra from the list we have discussed, and we have, I'm ready to show you, then if you take the commutator, you get one of these two Lie algebras. But it turns out there are a lot of left symmetric algebras which are not isomorphic. So it turns out that actually there are 10 exceptional 10 algebras without any parameters, and 2 continuous families with the parameters, right? And the complete list of normal forms, it is presented in 2 tables. We're ready to see them. In each table, what we do write. First, we write the name of the left symmetric algebra, then we write a structure relation. It means that we fixed the basis and we came up with a canonical form. It is a canonical form of our choice. It may differ from the form you like, but this is the canonical form we have chosen for this specific algebra. And we just write the multiplication table. That is, it means that we need to write eta 1 times eta 1, eta 1 times eta 2, eta 2 times eta 1, eta 2 times eta 2. We will write only non-zero multiplications. If some of these multiplications missing, it means that the corresponding multiplication is 0, okay, to shorten the table a little bit. And after you get this table of multiplication, we will write two operators. The R operators, this is like right action, and the left action of operator. I use this term right adjoined operator and left adjoined operator. I'm sorry, this is a typo. I should have deleted them because I decided not to use this terminology because it is already complicated as it is. So let's go to the list. This is the first list. B, the letter B in the name, means that if you take a commutative, if you take the associative Lie algebra, then it is not commutative. The letter C in the next table means that the corresponding Lie algebra is commutative. So we see here it is that, for example, B1 alpha takes any real number and goes like this. This is the multiplication. We see that we don't have eta 1, which means it's 0, and we do not have eta 1, eta 2, which means it is also 0. These algebras are not commutative. And we see that we have an L operator defined on this affine space, on this real algebra with coordinates x and y, and we have R operator, and this operator is Nijenhuis because this algebra is left symmetric. We will prove it, but it is supposed. So this table actually provides you with a good collection of examples of Nijenhuis operators in dimension 2. With some of these operators you have already met in lecture 4, which was completely dedicated to the case of dimension 2, which is an important case. And you can see that we have another family of the operators. See, this is B not equals 1, because if you put B equals 1 here, it still is a it is a Nijenhuis operator. But if you look at this multiplication table for B equals 1, you get this operation star becomes commutative, which means that it's not the B. So this beta not 1, it's not a very important limitation, right? It is just for the sake of the preservation, the idea that we separate the non-commutative case from commutative case. So B here can be 1, and you will get this C4. See, you get the algebra C4, but we go back. Okay, so we see that we have this algebra, this, and all this. Those two B4 plus and B4 minus, they are like the most interesting cases because they're there you get the most interesting pictures. I think in lecture 4 you've seen the lines associated with eigenvalues of these operators. They are very, very nice. Okay, and this is B5. It's trivial. It's Jordan block multiplied by Y. So then we have a case of C. Here it is. There's no structure relations. It means this algebra is identically vanished. It's a trivial algebra. Of course, we need to include trivial algebra. Trivial algebra is important because for our later work, it doesn't seem to be important now, but it is. Then we have a very simple like this, and these two nice algebras which have almost no non-zero multiplications. Okay, and here it is. As I said, this is the case of B1 beta for beta equals 1, right? You just get the commutative part. So to prove, we start with the preparation. The first thing what we want to do is we want to check that all the algebras in our tables, they are in fact, left symmetric algebras. We will do it using the theorem about left symmetric algebras and Nijenhuis operators. So we'll take this R operator, and we basically check its vanishing of its Nijenhuis torsion. For all these algebras from this list, the checking is trivial, because in lecture 4 you have shown that all the such operators are actually Nijenhuis. For example, if you look at this operator, then from the lecture 2, you know that if you take any function here and here, and depends only on y, then you can put any function f(x,y) here, and it is a Nijenhuis operator. And so it goes same for operators like this. If you have this, it is y here and 0 here, then you can put any function here. So basically you see that this operator is Nijenhuis, this operator is Nijenhuis, this operator is Nijenhuis, this operator is obviously Nijenhuis, this, and the only ones to check are C5 plus, C5 minus, B4 plus, B4 minus. To do that, we do this. We do the calculation. If you recall that in dimension 2, the vanishing of Nijenhuis torsion is the same as a relation between the differential of the trace and differential of determinant, and this is the relation we have written. The differential is written is a row matrix, right? And the action of operator on the row is written as by multiplication of the matrix from the right. This is what we do. Here it is. We just go and straight ahead check the determinant for B plus and B minus. This is what the plus and minus come from. You see it's at plus here, that is y plus here, and we have minus here, that is y minus here, and we apply this condition. We check straight ahead. If you multiply this by this, you will get that this multiplied by 0 is 0, then negative x times negative 2 is 2x, and you get this is 2x, and then x0 times 0 minus 2 is 0, so you get exactly the left side, and left side is a differential of determinant, and this is exactly the differential of trace. So basically you check, here it is, here's the same, and same goes for here, because you get the following. You'll get plus here for different reasons and minus here for different reasons. You will see it later, and you get that this works is the same way as this works. So all the adjoint operators are Nijenhuis. So in all the tables, all the 10 exceptional and 2 continuous filaments, they are in fact Nijenhuis operators. So that's what we know. Okay, the next step, first we have ensured that we've written in Nijenhuis operator. Why? Well, basically it's for the following idea, because later on we will do a very simple idea, is that we're trying to find a change of coordinates for an algebra with a certain properties to bring this algebra into the one form from the table. If we are not sure that the table contains only left symmetric algebras, then in the end of this process we need also to verify that the algebra we have after these procedures, right, is left symmetric, because we do not start with the left symmetric, we start with the different algebraic properties. Okay, but because we have already ensured, we've already done it for the tables, we don't need to do it in every case. So this is nice. So then next we proceed to the proof. Now what we need to do is we need to prove that all these algebras are not isomorphic. Why? Because, well, if you look at the same process I have just described, if you reduced one of the algebra to one point, to the one element of the table, and you reduced another algebra to the next entry of the table of these two tables, then what you basically need to do is you need to compare them. You need to ensure that your list is not only complete, right, but it is also contains pairwise, it is distinct, right? All these algebras are distinct, because you can come up with other different lists. For example, as I said before, if you take diagonal y, for example, and you put just function f x y, it is always an Nijenhuis operator. So you may say, well, this is a normal form. And this is bad, because what we need to do is we need complete classification, right? We need to, for this list to be complete and distinct. Okay, so that's what we're going to do. And how do we do that? Okay, how do we do that? First of all, it's a good thing we have not only R, but we also have L. Those are two operator fields. Now we deal simply with affine spaces, and we ask ourselves, when these two affine spaces have diffeomorphism which relates them and which takes the coordinate origin of one coordinate system to the coordinate origin of the other coordinate system. This is important because sometimes the operators, you can do the shift and those operators will become different. For example, in our case, the linear part, the constant part will appear, so we do not allow shifts. So it is a diffeomorphism with a fixed point. So I say, well, one affine space and other affine space are diffeomorphic, and the diffeomorphism takes one operator field into the other operator field. We say that in this is exactly the isomorphism of the algebras. This is what we've discussed, and it takes not only R, right, because it takes also L into L, because L also contains all the information, right, because it's linear with respect to coordinates. You can differentiate it and you can extract the structure relations, so from this operator. So basically they're supposed to be the same. Okay, now what is the obstacle for the operators to be diffeomorphic? Okay, as we deal with the operator field, we do have a lot of invariants. Those are the coefficients of characteristic polynomial, right? Of characteristic polynomial of both L and R. So basically what we say, we have four functions, right? We have trace, and we have determinant, and we have of R, and we have trace and determinant of L. So what we need to do, if the diffeomorphism exists, then those functions coincide, and if this diffeomorphism does not exist, and if these functions they do not coincide, that this isomorphism does not exist. So for us to prove then that those algebras in the lists, they are not isomorphic, we need to come up with functions, and we want to look for the functions which depend on these four. Again, trace R, trace L, determinant R, determinant L. Because if these functions they coincide, and these linear combinations coincide, and it turns out that the linear combinations are better to handle. So that's what we're going to do. So for example, we take a determinant L and go back to the table 1. Okay, see, table 1. So we take determinant L, and we see, well, determinant L identically vanishes here, right? But here, determinant L is 2y squared. It is 2y squared here, y squared here, beta y squared here, and alpha y squared here. And we see that it does not, it vanishes for, there's a typo, I think it's supposed to say that it vanishes also for alpha and beta equals 1. Okay, so but we will define this later. So we'll see that the determinant equals to 0 here, for beta equals 0 here, and for alpha equals 0 here. You see, right? So these identically vanish. So what we want to say is we'll take a look at these operators, and we see that for example, this, and these operators are totally not isomorphic to this one. Now we consider determinant R. It goes like this for determinant R. It vanishes here, and we see that it vanishes only identically vanishes only here and here, right? But it does not vanish here. So for we see that B5 and B1 alpha cannot be isomorphic, even if alpha is 0, right? Because if alpha is 0, then determinant of R is 0, but the determinant of B5 is always y squared. It's not almost zero almost everywhere. So in addition to the previous, we see that it cannot be isomorphic. Okay, and the same, and we see that the only one with a vanishing determinant is this one, right? So then we proceed like this. We take operator field L for we take a look here not only on the functions but with algebraic properties. For example, if we look at this operator, for example, we see that this operator is diagonal. It can be brought for alpha not zero to the diagonal form, right? And for this operator, it cannot be brought to the diagonal. I'm sorry, no. I'm sorry, I'm looking at R. I'm supposed to be looking at L. So if we look at this operator, it is diagonal, right? And this operator, it's Jordan block almost everywhere, right? So even for different lambdas, this is diagonal everywhere, and this is diagonal only for y equals 0 because it is 0, right? So they cannot be isomorphic because this implies that the Jordan property, the Jordan structure coincides, and we know that when we have a diffeomorphism, then Jordan structures coincide. And we proceed like this. We define the function like this to separate the different functions for the same collection of B alpha, right? For different alphas, those algebras are not isomorphic because we take function like this, and it is identically vanished only if this parameter of alpha equals to alpha 0, and if it's not alpha, then this is not identically vanished. But we see that this is a linear combination of those invariants, and this is this property is supposed to hold everywhere and for the entire algebra. So same here, we go over the different functions, and we see that the is supposed to be the typo here. It's supposed to be beta equals beta 0 here, and we see that the algebras are not isomorphic for different betas, and we see that pairwise they're not isomorphic. And then proceed to the table 2. Table 1 and table 2 are different because they give us one gives us left symmetric algebra with commutatively algebra, and the other gives us left symmetric algebra with not commutatively algebra, so they cannot be isomorphic. Okay, so then we proceed with Jordan blocks and different theorems. The table 2 seems to be easier. You can just carefully look at it and see, well, this is identically 0, which means it cannot be isomorphic to any of these. Then if we look at this operator, the determinant is not 0, and determinant is not 0 here, and determinant is not 0 here, but here these are identically vanish. That means that any of these 3 cannot be isomorphic to any of these 2. Then we look at these 2 operations, then we see, well, look, this is diagonal, right? And this is Jordan block almost everywhere. For y equals 0, it is 0. It's not. So they cannot be isomorphic too. So these 3 are pairwise not isomorphic. Now we look at this, right? We take a discriminant of characteristic polynomial. We see that the discriminant identically vanishes here, but it does not vanish here and here, which means this algebra cannot be isomorphic to any of this one. And here we see that if we take a discriminant of the characteristic polynomial, we'll see that the discriminant is okay. It means that it's always positive because it will be square, and here it can become negative, right? So these 2 cannot be also isomorphic. In case of C, it is better and easier to check just by looking at the table, but you can carefully do that. Okay, so now we proceed to the next step. Before proceed to the classification, splitting our case into a different number of cases, we will need 2 lemmas. We'll keep them in mind while working. One is as follows. Imagine that if you have a pair of operators just in arbitrary dimension, you commute them, and you get the same operator Q with some lambda which is not 0. Like, for example, this identity holds. Then it turns out that Q must be nilpotent. Why? Well, it's a simple observation, because if you take this commutator once, and you take this commutator twice, and you take this commutator 3 times, if you define an operator called an adjoined operator, you will see that different powers of Q, they yield us, because the commutator of matrices, it is actually a derivative of multiplication. We see that it gets us different eigenvalues. If it does not vanish in any power, then in each power it yields us new eigenvalue, lambda, 2 lambda, 3 lambda, and so on. But this operator, it's actually finite dimensional, so it cannot have infinite many eigenvalues. So at some point this thing must be 0, right? And when is it 0? When, because n and lambda are not 0, it means that q in power of n is 0, right? So it's a simple observation, useful, naturally appears in many different things. The other is a two-dimensional commutative subalgebra contains one-dimensional subspace spanned by identity matrix. It's a simple observation that if you look at matrices 2 by 2, then this algebra is not commutative, and the maximum dimension of commutative subalgebra is 2. It is a Schur's theorem. It's a very famous theorem in arbitrary dimension. It states that if you have a GLN R, then you need to take n squared, like divided by 2, and take the whole part of this number. Then you need to add 1, and this is the dimension of the corresponding maximal dimension of commutative subalgebra. And here it implies that if your commutative subspace, it does not contain the identity, then you can add the identity and you get a commutative subspace of dimension, subalgebra of dimension 3, which cannot happen by Schur's theorem. Okay, so those two lemmas, they will use them. So now we need to split the algebras into different parameters. So let us recall that left action, it defines actually the morphisms of Lie algebras. It means that you can represent your algebra in a 2 by 2 matrix, and we look at the dimension of the image, right? Because, for example, if algebra is commutative and if algebra is trivial, then all the matrices 2 by 2, they're all 0, right? So the dimension is 0. And if the dimension is 1, those matrices are 2 by 2, but still they all are linearly dependent, which means that the image has dimension 2. So the dimension of representation is always 2, because it is the number of dimensions of your algebra. But the dimension of image, it may be 0, 1, and 2, because algebra has dimension 2. Then at most the image of the dimension is 2. In this case, the representation is called faithful. Okay, we start with the most degenerate representation. We start with the most degenerate cases because they seem to be simpler. Okay, so we start with the most degenerate case, like n equals 0. In this case, we have that left action identically vanish. It means that we have a 0 operator field, which means that the algebra is 0. It is C1. Okay, this identically is 0. It means that all the multiplication is trivial. Okay, now we have now a dimension of image equals to 1. What does it mean? It means, as I said before, that all the matrices, they are linearly dependent. So what we do is we say, well, look at this formula, right? And we know that this map has a kernel, right? This map has a kernel, because if the image has dimension 1 and pre-image has dimension 2, then there is a kernel. So we can, without loss of generality, we assume that one of our coordinate vectors is in this kernel. And this means that this left action is the kernel, which means that this matrix of left action of Xi1 is 0. It means that Xi1, Xi2 is 0, Xi1, Xi1 is 0. This is the relation, right? But we do know that if this matrix is 0, then this also 0, which means that because of this representation, that means that xi1, xi2, right, because of this, lie in the kernel of L. See, here this is 0 matrix, then this is 0, but by left symmetry, we have this condition, right? And this implies that this is supposed to be from the kernel of the L, which implies that if we commute xi1, xi2, we need to get a vector which is collinear with xi1. And this gamma is a parameter which we add to our formulas. If gamma is 0, then those two commute, and we get, as I said before, xi1 times xi2 equals to 0, but they commute, so xi2 times xi1 is also 0, so we have all the zeros. And for xi2 times xi2, we do not actually know anything. So we just take two parameters b and a, and write them in this formula. So basically, this is what we're starting. We're already using some information from the fact that we deal with the left-symmetric algebra. This is the fact, and from dimension of the image, right? From this fact, we've established that it's in some coordinates the structure relation, they're like this. Now what we do, we try to kill off as many constants as we can and see what constants cannot be killed off, right? So what we do, we take the case, for example, a is not 0. This a is not 0, right? This coefficient. So if a is not 0, then we come up with a coordinate change, which goes like this, and we multiply it. Now imagine if we multiply eta1 times eta1, this will be xi1 times xi1, which is 0. If we multiply eta1 by eta2, it will be xi1 xi1 here, xi2 xi1, or other way around, xi2 xi1 xi2. Both are 0 because of this condition. So we see that after this coordinate change, we did not change first coordinate vector, but we changed the second with some coefficients we came up with, let's say, on the hunch. We see that this formula holds, right? So there's first three structure relations, they did not change. But if we multiply it by this, we'll see that, well, the xi2 times xi2 survives. It goes like this, and then you apply this formula. You substitute this formula into xi2, xi2, and you get the following formula, which is exactly eta2. So we came, after this coordinate change, we see that we killed off all the constants, in case of a is not 0. See, we get that all those three, and eta2 equals eta2. Okay, this is exactly C2 algebra. Then we go step by step. We assume that a is 0 and b is not 0, and then we come up with a coordinate change and we get C3. And then we arrive to the case when gamma is not 0. So we say that after a coordinate change, we assume that this can be, we can change the coordinates to get gamma equal to -1, which is a very simple coordinate change. It goes like this. See, so without loss of generality. And we say that, well, we have these new coordinates, right? The difference from the first two was here that we had a 0, and here we have that xi1, xi2 is 0, and xi2, xi1 is xi1. And we again have two constant, and we go all over again. We start with a is not 0, a is not 1, because it's not 0, and we come up with a coordinate change like this. We perform a calculation, and we get b1 alpha. And then we take a equals 1 and b equals 0, and we get the following algebra, which is already b11. And finally, if a equals 1 and b is not 0, right, this is the last case, then we come up with the following coordinate change, and we get b5. So we see that after all this work, we basically checked the several cases. How we did that? We assumed, like, we came up with a draft of structure relations, we wrote them, and then we say, well, different parameters of gamma yield us different drafts, And in each draft, we killed off coefficients, at least some of them, by coordinate change. And we see that the result, they all lie in our table, and they all are Nijenhuis. It means that all the algebras are left-symmetric, because we didn't need to check it, because we've already established this earlier. And then isomorphic, we've established this earlier too. So now the second step is n equals 2. So basically we say that the representation is faithful, right? It has no kernel. We have actually two cases: the case of commutative associative Lie algebra and non-commutative associative Lie algebra. And the non-commutative is of course split also into cases, which both are complicated. So we start with the commutative. What we do here? Here we do a little bit of preparation. First of all, we use second lemma. We didn't use it yet. What we say? We say, remember that in any commutative space you have a identity matrix. So it means that if we have two-dimensional commutative space, because the representation is faithful, that we get two linearly independent matrices and they commute, which means that at least linear combination of them is an identity matrix. So without loss of generality, we assume that we've chosen the basis such that the image of the second basic vector is identity matrix. We again check this, and we get that this vanishes, and we get that this this case is 0, right? So we say that representation is faithful. So of course these basis vector fields, they do commute. Okay. So if they commute, right, we have the following. We see that what do we know? What does this identity means? It means that if I apply it to psi1, I get psi1. If I apply it to psi2, I get psi2. This means that we already have, after this, using this lemma, we've already have the following. We have psi2 times psi1 is psi1. Psi2 times psi2 is psi2. And because of the commutativity, right? Because of the commutativity, we get that psi1 and psi2 is equals to psi2 times psi1. So we get this again, and we again get the draft of structure relations, right? Again, with the different A and B's. And in this case, we've split them like this. First, we assume that this this number is not 0. It turns out that you'll need to take a square root of this number, to take a model of this number, and you do the coordinate change, and the coordinate change is like this. And if it's 0, then it's a good coordinate change, and this thing vanishes. See this, and because in this sum, this plus this, it's plus this. It's because this is 0, it vanishes, and we get that this is C4, right? This is 0. And then if it's not 0, then we come up with a very which looks kind of complicated, but it's not. You just need carefully to adjust the constants for you to get to do the trick. See, it turns out that all these are the same, and if you multiply them, you get like this. You get the sign of this number, which it turns out these relations, they for the positive sign, they give us structure relation for C plus, and for negative sign, they give us structure relation for C minus 5. Those simple algebras. Now we get, we assume that the associative algebra is not commutative. Here, first, we use that in the appropriate coordinates, the Lie algebra has a very specific form, right? So, and especially this form, right? That's what we discussed. Because the representation is faithful, it means that because this commutator means that L with a commutator in low indices, because of left symmetry, we get that the following condition holds. So, because there is only 2 Lie algebras, we've already established that psi1 times psi2 minus psi2 times psi1 is psi1. Okay, now by lemma we have proved earlier, we know that this operator, it cannot be it is nilpotent, and nilpotent operator is in dimension 2 is very simple. It has kernel and image, they coincide, and thus we actually have two cases, right? We need to understand this image and kernel, is it spanned by different vector or by the same, because here we have a vector. The first case is we take psi and assume that it's spanned by psi1, and this is the formulas we get. These are the relations, and this actually implies that L psi1 times psi2 must lie in the space spanned by psi1. So we get this. From this commutativity, we get this. And because the kernel is coincides with the image, so this we get this. So this is the draft of the structure relations, but we see that we have more coefficients than we need. We have gamma A and B. So we apply the left symmetry condition. See, this is the first time we straight ahead do the left symmetry associator. We actually did use the condition which relates left action with Lie algebra, but this is the first case. We just calculate the associator straight ahead and get the restriction like this. We'll see that this number is supposed to be 0. We know that this is not 0, because in this case, if this 0, then L psi1 must be identical 0, because it vanishes on it sends psi1 to 0 and it sends psi2 to 0, because left psi1, L psi1 is multiplying psi1 from the left side. So gamma cannot be 0, so B equals to gamma, thus for this to vanish. And we get the following final draft. It already have 2 coordinates. And then we go and proceed by choosing different variants. So gamma 1 A is not 0, gamma 1 A is 0, and gamma is not 1, then we come up with a change of basis, and we get B to beta. Okay, and now the finally is we take again the image. See, recall we in the first case we again, this operator is Nijenhuis. I'm sorry, this operator is nilpotent, and we know that the image which is a kernel, is spanned by the following vector, where A is some non-zero constant, which we use here. We do some work. We see that if we apply L psi1 to psi2, then we get something like this. If we apply psi1 to psi1, we get something like this. And because B is not 0, right? Because psi1, it does not lie in this linear space in the kernel, so it shouldn't be 0. Thus B cannot be 0, right? A here can be 0, but B cannot. So if B is not 0, then we do pre-change of coordinates, which goes like this. See, it's always a good change, because even if A is 0, then we have psi2 and psi1, and this coefficient is not 0. And we get that eta 1 times eta 1 is sine B. Means that it is important, the sign. And we apply the commutator, and we get, and applying the left symmetry 2 times, we get the following, that the gamma equals to 2, and we get the relations like this. Those are the final relations. So see, the last one took the most work, because we had to come up with the different drafts, and that's what we did. And then we see that if the sign is 1, then we get B plus, and the sign of -1, we get B minus 4. Those are the last 2 left symmetric algebras. So you can you will be able to go through this proof in details. You can see I outlined the most important spots, right? So you've got the idea how it is done. It is done. It's not a very complicated. It's a very careful work, and it is done in many steps. You see that the steps are parameterized by the dimension of image, and in the last case they are also parameterized by whether you have a commutative or non-commutative algebra. And in case of non-commutative algebra, you again have 2 important two important cases when the image is and the kernel is spanned by some vector, and if it's not. And all the others are just taking different values of parameters and coming up with the coordinate changes. Here it is two exercises, which are nice, because if you look at C plus 5, let me show you. Let's go back and look at the table again. So if you look at this table, it is a nice exercise to show that basically it's a very simple algebra in disguise. It means that you can change the coordinates, and this becomes a direct sum of two non-trivial one-dimensional algebras. It means that the operator R will be x, 0, 0, y. It means that x, y on diagonal. And if you apply, and if you look at this, then it turns out that this algebra is in fact, this is what you need to prove. This is the first exercise to prove that you actually can do such a coordinate change. And here, what you need to prove is you need to prove that this is just a real version of the complex one-dimensional complex algebra. If you take one-dimensional complex non-trivial algebra, that is eta times eta equals eta, and you go back to the field of real numbers, this is the two-dimensional algebra you get. Okay, I think that's it. That's it. Okay, these are exercises. Any questions? Okay. If there are no questions, thank you. Thank you very much.